Welcome to the tutorial section based on lecture number 9, Central Forces. So here we have few problems. So let's try to tackle them one by one. So in our first question we have, which of the following is true regarding the motion of a particle in a central force field? So here we have the first one, the motion of the particle is confined along a straight line. That's not necessarily true. That's because only says that when you have a central force, the force is given by a function of r times r cap. Let's say that for a force to be central in nature, it has to be acting radially. That means along the line that joins the fixed point O and where the particle is present. This is only dependent on this thing. However, this is saying, it says nothing about the motion of the particle. So our first one is not correct. Now coming to the second one, motion of the particle is confined in a plane. That is actually true. The reason being, let's come to C as well. The angular momentum of the particle is conserved. This is true because it's true that when we have motion, we know that for a central force, the rate of change of angular momentum, so that's equal to 0, and this implies that our angular momentum is conserved, or that means it is constant. And when we say this is constant, that means the direction as well as the magnitude is fixed. Here the angular momentum of the particle is conserved. Now coming to the motion of the particle, we know that L vector is given by mr squared theta dot, and we have the vector which is r cap cross theta cap, and this means that our L vector is perpendicular to the plane that contains r cap as well as theta cap. So that means r cap and theta cap, which together constitutes the motion of the particle, and that's happening on the plane because L vector being a constant. So that means r cap and theta cap is always going to lie on a fixed planar surface. So our motion is going to be confined to a plane. So our B is correct. However, we have to pick only one option out of all the 5. So since B and C are correct, so the actual answer is going to be option number D, where both 2 and 3 are correct. So this is the correct answer. Only one single option is correct. Let's move on to the next problem. Problem number 2. So we have a system whose angular momentum is given by L vector equals to the cross product between the radius vector and the momentum vector. And this particular system is under the influence of a central force field F. The question is, how does our angular momentum L vector changes over time? In fact, the question that we have been asked is, what is dl vector over dt? Now we know that L vector is given by r vector cross p vector. That's already given in the question. If we take the time derivative of both sides, so we have to take the time derivative of r cross p, so that will be dr vector with respect to time t crossed with p vector plus r vector crossed with dp vector over dt. We know that dr vector over dt, that's simply v vector, and p vector is a m times v, that's the expression for the linear momentum, plus r vector cross now dp vector over dt, so that's simply the force field f of r times r cap. Now clearly we have v vector cross v vector, which is 0 because they are acting in the same direction, plus we have r vector crossed with r cap, which is also in the same direction, so that's also 0, which gives us that dl vector over dt is equals to 0. So there is no rate of change of angular momentum. So our first option, L vector linearly changes. No, that's not true. If we look at all the options, so we have option D, which is correct, that L vector does not change over time. Let's move on to the next problem. Problem number 3, of the following which could be the example of a central force field? If we look at all the examples, only the force due to an electric field is the example of a central force field. So B is the correct option. Problem number 4. Consider a central force which is given by this particular expression, and we need to check which of the following is true. Now looking at the option, A and B can be rejected. The reason behind this is that until and unless we know about the sign of our force vector, we cannot say if it is attractive or repulsive in nature. Also, if we look at option number E, it's saying that the radial and the angular part of the force is non-zero. Now from the expression of the force, here we have force given by some number times r cap. So r cap means it's the radial part. We do not have the angular part here. So definitely this is the definition of a central force which only has a radial part. So its radial part is non-zero, but there will be no angular part. So we can reject option E as well. Now coming to part C and D, which one of them is true. Now let's take some values. So for r lying between 0 and 1, suppose we take the value r is equals to half. And let's substitute this value. So our force vector will be equals to half times, so we have half minus 1, so that will be negative half, divided by, we don't have to worry about the denominator, that's always going to be positive in nature, times r cap. So this is giving us negative r cap, which is only true when we have a attractive force. So that means for r lying between 0 and 1, we have a attractive force. Now let's say if we take r value greater than 1, we'll take, let's say r is equals to 2. In that case, if we substitute the value of r with 2, we'll see that our force is going to be some positive values times r cap, which means it is repulsive in nature. So that means option C is going to be correct here. Let's move on to the next part. Problem number 5. So here we have a force field which is given by this particular expression, and this force is a central force field. Now using this information, we need to obtain the potential function that corresponds to this particular force field. So usually when we have a force field which is central in nature, that means such forces are conservative, or we can say that such force F vector are given by the negative gradient of some potential function phi. Now since F vector is along our radius vector, so this will be simply f of r is equals to negative del phi over del r. A potential function phi will be the negative integral of f dr. Now f dr, that means we have to take the radial part of force vector, so that's alpha over r squared plus beta over r cubed times dr, and when we integrate it, we get alpha over r plus beta over 2r squared plus some constant of integration. And if we look at our options, so we see that our option D matches with the one that we have just obtained, so this is the correct answer. Let's move on to the next problem. So here we have the following equation: theta dot equals to omega, which is a constant, and r equals to r naught times e raised to the power of beta times t. And this particular two equations describes how a particle moves along a spiral. The first task will be to find an expression for the acceleration. So let us begin. So here we are given that theta dot, which is d theta with respect to time t, or d theta over dt, so that's equals to omega, which is a constant. When you solve for theta, so that's d theta equals to omega dt, we have theta is equals to omega times t. So this is our expression for theta, and we have r, which is given by r naught times e raised to the power of beta t. So these are the two equations of motion. Now we will use r to obtain r dot, which is simply dr over dt, which will be equals to ddt of r. So that's simply r naught e raised to the power of beta t. R naught is a constant, so we have r naught times differentiation of the exponential function, which is the function itself, times, we have to use the chain rule. So that means we need to multiply it with the differentiation of beta times t, beta being a constant, so that gives us beta r naught e raised to the power of beta t. So this is a r dot. So we'll replace r naught times e raised to the power of beta t with our value r. So this is equals to beta times r. Now we have r double dot, so that will be equals to d dt of beta times r. So we have beta times r dot, and again replacing r dot with beta r, so we get beta times r beta squared times r. So this is r double dot. Now to find an expression for the acceleration, we know that the acceleration has two parts, the radial part as well as the angular part. So we have r double dot, this is the radial part added to the angular part. Let's substitute the value. So we have r double dot, so that's beta squared r minus r times theta dot square, so that's omega squared times r cap plus 2 times, so we have r dot, so our r dot is beta r times omega, so we have beta omega r plus r times theta double dot. So that means this is, okay, we haven't found out the value of theta double dot since this is a constant. So theta double dot is simply equals to 0. So this is 0 times theta cap. So that means our final expression for acceleration will be given by, so acceleration is equals to, we'll take r as the common factor, so that will get multiplied to beta squared minus omega squared times r cap plus 2 beta omega r, and this is the angular part theta cap. So this is the expression for the acceleration. So now that we have the expression for acceleration, part 2, we need to find out the force equation as a function of r when the beta value is equals to omega. So in order to find out the force equation, we start out with the equation of our radius. So r is equals to r naught e raised to the power of beta times t, and since we are given that beta is equals to omega, so we have r equals to r naught times e raised to the power of omega t. So this is our first equation. Clearly we see that r is a function of time t, but what we want to do, we want to express r as a function of theta alone. So that means let's take our theta dot, which is omega, that is a constant, so that means we have d theta over dt equals to omega, which is equals to d theta equals to omega dt. Now if we integrate both sides, so theta will be going from theta naught to theta, and time will be from 0 to t. So that gives us the value of theta. Theta minus theta naught equals to omega times t. So we'll replace omega t in the r with theta minus theta naught. So that means we now have r equals to r naught e raised to the power of, so we initially had omega t, so now it will be theta minus theta naught, and we can see that r is now expressed as a function of theta. Now we need to change the variable from r to u, so we will use that r is equals to 1 over u, so that means our u will be equals to 1 over r, and that's 1 over r naught times e raised to the power of theta minus theta naught, or simply u is equals to 1 over r naught times e raised to the power of negative times theta minus theta naught. So this is our u's. Now that you have u as a function of theta, what we'll do, we'll need to find out du over d theta, and we will also need to find out d squared u over d theta squared. The whole idea being, we have the differential equation, which is d squared u over d theta squared plus u is equals to negative m over u squared L squared f of u. So using the value of du over d theta and d squared u over d theta squared, we can find out the equation of force as a function of r. So let's do that. So we'll take u and differentiate with respect to theta. So we have 1 over r naught, so that's a constant, times e raised to the power of negative theta minus theta naught. And using the chain rule, when we differentiate negative of theta minus theta naught, that gives us negative 1. And since this value is u, so we have negative u. Right. And again, differentiating both sides with respect to theta, so we have d over d theta of du over d theta, which is negative u. So that's equals to negative of du over d theta. And we've already obtained the value of du over d theta, which is negative u. So we have negative of negative u, but that gives us positive u. Now let's substitute all these values. So we have positive u plus u equals to negative m over u squared L squared, and f of u. When we solve for f of u, we should get negative 2u cubed L squared divided by m. And finally, in order to obtain expression for the central force as a function of r, so we replace u with 1 over r. So this will finally give us f of r equals to negative 2 L squared divided by m r cubed. So this is the expression for the central force. So let's look at the final problem. We have an equation of motion given by r equals to negative at and theta equals to negative b over t. Here a and b are constants, and we need to prove that the above parametric equation represents a central orbit. So let's do that. So here we have, let's start, r equals to negative times at and theta is equals to negative b over t. So what we do is let's take the time derivative of r, so that will be simply negative a, and again time derivative of r dot, which is r double dot, so that's equals to 0. Now coming to theta, time derivative of theta will be theta dot, which is equals to b over t squared. Our next task will be to show that the equation represents a central orbit, so we'll work with the angular momentum. So the magnitude of the angular momentum is given by m r squared theta dot. We need to show that this value is constant. So let's take, so we have m times r, so r here is negative at whole squared times theta dot. So theta is b over t squared, which is equals to m times a squared t squared times b over t squared. So the t squared gets cancelled, and that leaves us with m times a squared times b. A and b are constant, that's already given. We will consider mass to be constant for the particle. So this is constant, and because our angular momentum is constant, we know for sure that these two equations, r equals to negative at and theta equals to negative b over t, represents a central orbit. Now the next task will be to find the force equation. Right. So we will start with r equals to negative at. So we have r equals to negative at. Now clearly here we see that our r is expressed as a function of time t. Now what we'll want to do, we want to express r as a function of theta. So we have theta is equals to, theta is given as negative b over t. So let's take r and multiply it to theta. So r times theta will be, so for r we have negative at multiplied to theta, which is negative b over t, which is equals to ab. So that means our r is equals to ab divided by theta, and this is clearly a function of theta. So this is the expression for r expressed as a function of theta. We'll use this equation to find out the force. So let's use it. So we are going to make a u substitution. So we're going to suppose that r is equals to 1 over u, such that u is equals to 1 over r, which is equals to theta divided by ab. Let's take the derivative of u with respect to theta. So that's simply 1 over ab. And when you again take the derivative of du over d theta with respect to theta, so that will be 0. Now coming to our force equation, we have the differential equation d squared u over d theta squared plus u. So that's equals to negative m divided by u squared L squared times f of u. So let's substitute all of this value here. So d square u over d is theta squared, so that's 0, plus u is equals to negative m divided by u squared L squared f of u. Solving for f of u, we have negative u cube L squared over m, but we want our function force to be a function of r, so we replace u with r. So that finally gives us f of r equals to, we have u cubed in the numerator, so that will be L squared, negative L squared divided by m r cube. So this is the expression of our force, the central force. Thank you.